Let's take a look at where power goes in a computing system. So first we'll start off and take a look at a server CPU. So here's where a server CPU spends its power. So the 8 cores on the CPU are just under half of the power. You can see how much power each core is. The level 1 cache, the registers, and the TLB take up about 1/6 of the power. So does the L2 cache and the L3 cache. So what you see here is that an enormous amount of the power is used in the memory hierarchy. About half the power in the memory hierarchy, half the power in the cores for a server CPU. Now, a question about this: why is the energy in the L3 the same as the L2? Well, the answer here is that the L3 is much larger. Even though it's accessed much less than the L2, because the L2 filters requests to it, it has enormously larger energy because it's just so much larger. So let's take a look at that. Here's an Intel Sandy Bridge 8-core processor. Here's the L1 and the L2, and here's the L3. So every access to this L3 has to access and move data somewhere in this huge array, and that just costs enormously more enormously more energy. So even though this device, the L3 cache, is used much less frequently because each access costs so much, it's still a very big source of power. Let's take a look inside a chip. So this is from a GPU from NVIDIA, and what we can see here is that doing the computation, doing the work, this is a very small amount of energy, 20 picojoules for 64-bit double precision fuse multiply add. Tiny amount of energy. If we look at reading the data from an SRAM, it's a small memory, 8 kilobytes, this is twice the amount of energy as actually doing the computation. So reading the data is more energy than doing the computation. If you look at moving the data costs anywhere from the same amount as doing the computation to 25 times as much if you want to move the data all the way across the chip. So moving the data is extremely expensive. And this is inside the chip. That's because these are very long wires, and in order to move the data across them, you have to charge up this entire wire to send the data and move it across there. And that's a lot of charge for a long wire. Let's take a look if we go off chip. So if you're going to go to DRAM, it's costing you 800 times as much energy as it does to do the actual operation. So this is incredibly expensive. This means that if you have to access data that's off the chip, it really doesn't matter how much energy it takes to do the computation because you've spent so much just getting the data. Now, you can do much better than this. So current off-chip accesses are not very efficient. If you make more efficient links with custom memory solutions, you can be much better about this, but it's very hard to get the industry to adopt these because memory is such a commodity. That means people make it just for the cheapest part, not for the best performance. Let's take a look at a data center. So here's a graph about how energy is used in a data center depending on the load on the machine. So what we see here is that the CPU is only half of what's going on there. And this is why everybody wants to build custom hardware for the data center. Can they put this together and get the right mixture to bring this down? Because it's not just the CPU, there's all this other stuff. So this is why Facebook and Google are all building their own storage systems and networking and the like, so that they can try and reduce these other parts up here. Another interesting thing to look at is down here in idle. Here's an unused machine, and it's still wasting 50% of the energy of one that's running at 100%. This is really inefficient given how often machines run idly, and this is why data centers have been spending a lot of time figuring out how can we make sure our machines aren't idle, and why server vendors are spending a lot of time how can we save power when we are idle. So Intel has made a huge stride here in basically taking this idle power when the machine is idle and cutting this down to very close to, well, not close to zero, but much lower than this. So they've been working a lot on that. All right, so here's a question about power efficiency. Which one of these would you say is best? You've got 3 different devices here. They run different amounts of performance and different powers. Which one would you say is best for you? So I would say this is not clear. You can go do the math, and you can see that the GPU has 15.6 gigaflops per watt. The CPU is much lower at 3, and the SoC here is up at 58 gigaflops per watt. So this is clearly the best in this sort of normalized efficiency, but it really depends on what you're doing. So if you need double precision math, well, then the GPU wins for you. If you need more than 12 gigabytes of RAM, then the CPU is going to win for you, even though it's less efficient. So it really depends on how you're using these things. So efficiency is something you should look at a given point, and you want to be careful about normalizing it. So looking at efficiency for a server machine, you're looking about 200 watts and you have specific requirements on memory. If you're looking at a laptop, that's a very different design point, and embedded is another very different design point. So the point of this analysis here is to point out that normalizing gets rid of the domain and makes things unreasonable. So this device may look really good for doing double precision computation, but you couldn't possibly fit this into a mobile device, so you really can't do that comparison. You can't compare these numbers directly without losing the information about what the capabilities and domains are. So you need to be very careful when you're looking at power efficiency and normalizing things.